Hello, good afternoon. Welcome to the fourth installment of this MICGen series. It's a series of online events that we are holding at CICAM to promote the participation of early stage researchers that are suffering from the difficulties to hold or to keep scientific exchange during this period of this coronavirus crisis. So we are organizing, events with presentations by a well-established researcher and then also young researchers and then a more interactive poster session. And today, the topic is about data-driven science. And it's a pleasure to introduce people who are here today. First of all, Sarah Bonella, the Deputy Director, and myself, we are in charge of organizing the event. And we have the more experienced lecturer, Claudia Draxel from Humboldt University, Berlin, who will speak first, and then afterwards we'll have a presentation by Aram Hospital from the Institute of Biomedical Research in Barcelona, and Pierre-Paul de Broek from the Université Catholique de Louvain. And I'm sure we will be looking at complementary aspects of data-driven science. And we try to ensure and enforce as much as possible the interactive character of the events that we share, we organize typically at CICAM. So let me see if I can share the screen before we start this first part of the session today. I don't know if you are looking at my. No, that's you. Is it okay? Are you looking at the PowerPoint?
Yes.
Yeah. Okay. So yes, before starting, I wanted to comment on a few points so that we organize ourselves in how we ensure this interaction. First of all, we will be recording this first part of the event. Actually, later on, it will be available on the CICAM YouTube channel if you want to come back and check or revisit some of the presentations or the discussion. I would say in order to focus the interaction, the video is not activated, and also you don't have the chat feature between participants in such a way that all the interaction is channeled through the Q&A button that you have on your Zoom window. Now, for the first talk, the lecture given by Claudia, that is more extensive or longer, there is the possibility to ask questions during her presentation. During this part, when she is talking, then if you want to make a question, you should write your question in this Q&A window, and then I will see it and I will relay that to Claudia so that it does not really interfere with the flow of her talk. And then remember that in any case, once the talk is finished, then there is devoted time for questions and answers. And in that part, there you do not need to, still the interaction is through this Q&A channel, but you don't have to write down your question. You can simply indicate, I want to ask a question. And then once we see, that will appear in order, then we will, I will receive you will receive a notification to unmute yourself. I will then ask you to ask the question, then you can ask the question live. And I think that also facilitates if there is the need to deepen the discussion or enrich the then you have the possibility really to enter in a dialogue with Claudia. For the second and the third talk, because they are shorter, then we will allow both speakers to make the presentation, and then we reserve all the questions to the end of, and the process of the Q&A is the same that I was describing. So you simply indicate you want to ask the question, then I will indicate when you can unmute yourself and then ask the question. Okay, so I hope this clarifies how to interact, and it's not really the same as being face-to-face, but let's try to make it as interactive, as lively as possible. So we'll now start, and we move with the first talk by Claudia. So now, Claudia, the floor is yours.
So thank you very much, Ignacio, for the introduction, and also to Sarah and you for putting together this very interesting format. I'm happy to give you a little guided tours about how you can get from data to knowledge, and I'll address quite a few aspects of this that you see in the next transparency. In any case, I think this topic is very much related or very often happens in the cloud, right? So data science depends a lot on the cloud, and that's why I have brought quite a few clouds with me, but also a lot of sunshine, I hope so, and I hope you will enjoy it. I think we all miss sunshine and clouds and traveling, so I like to give you a little bit perspective on future times as well. But let me focus on my clouds. So the aspects that I like to address here is the scientific vision that we have, which knowledge do I like to address. I like to address also research paradigms, fair data collections, high throughput calculations, sorry, artificial intelligence. I'll also talk a little bit about trash, but don't worry, this trash won't be smelly. So overall, I'd like to take you through a little guided tour, as I said, but I'd like to start actually with discussing what the physics is that we're doing today. So how does our daily research look like? And for this, I'd like to introduce my group to you. Sometimes people do it at the end, I do it at the very beginning. So as you know, I'm a theoretical physicist, so all my group is performing calculations, but probably before that, they derive equations, they program these equations to put it into computer codes, such that at the end of the day, they can apply all this methodology and the codes they develop to focus on research problems for quite a number of interesting materials. So what do they have in common, and what do all of us have in common? This is our aim to publish at the end of a PhD thesis or a master thesis, or at the end of a year or whatever, nice papers, right? And I would like to zoom into one of these papers just to address our style of research and the style of publication. So this is a paper on thermoelectrics, and well, obviously I'm not going to talk about the content of the paper, but I would like to address here how we publish, right? So at the end, what you find in a typical paper, that would be a table, that would be a figure, that would be a structure, that would be probably a few other numbers that we have extracted from all the research that we have done over this period of time. But in essence, we never provide all the information. I think that's perfectly fine, because nobody wants to read a paper that's 100 pages long, and nobody wants to write a paper that's 100 pages long. So I think the way we publish is perfectly okay, but we have to complement this, because overall, if you keep investigating one material after the other and looking at one method after the other, then our daily research is great. I really love it, but overall it's a slow process, considering that we need materials for all kinds of applications very urgently. So let's imagine that we don't do this one by one investigation, but someone, a ferry or whatever, gives you all data from all calculations that have been performed over the world. This would give us a lot of information, and we could extract much more knowledge from that, rather than just staying with the realm of one paper or one research group. So to give you an idea what this means, I like to walk you a little bit through the data structure that we're talking about. So talking about thermoelectric materials, this was the paper about, typically, let's say, number in order to access whether a material is useful as a thermoelectric or not, is the thermoelectric figure of merit. So what do we need to do in order to compute one number? This is just one number, right? So first of all calculations that we perform need to be performed over a whole temperature range, because thermoelectricity means recovering waste heat, and that's why thermoelectric devices, they have to operate over a large temperature range. So the properties we need to compute is the geometry of the material. These are phonon spectra in order to get thermal conductivity. This is the electrical conductivity, because at the end, thermoelectric figure of merit is the ratio between electrical and thermal conductivity. And now if you look at the middle column here, then you will realize that you also need to involve quite a variety of methods, which would be density functional theory for the geometry, for instance. You would use many body perturbation theory, for instance, to compute electrical conductivity, phonons with density functional perturbation theory, or even better molecular dynamics to get the thermal conductivity and the phonon spectra. So, and if you look now at the right-hand side, you see that we have created just for one material, probably terabytes of data. And so the question is, if we summarize now what goes into one publication, several years probably of person work, several million of CPU hours perhaps, many terabytes of data, just creating the information about one material. And of course, these terabytes of data, they contain a lot of information and a lot of insight, but it's much more compared to what we publish in a manuscript. So the natural question that arises here, is it worth doing the same again? So is it really needed that a new student starts again from scratch? And this is the first trash bin I have brought with me, so to say. I think at the moment, I think most of this data that are computed, they go to the trash. They are simply thrown away when the student finishes the work or goes away. So, but we need to keep this data in mind, because as said, they keep a lot of information. So, but let me get now to my clouds. And this actually brings me right away to fair data collections. This was actually the reason or why we established the NOMAD, the Novel Materials Discovery Laboratory. Right? So it was established as a bilateral project between Matthias Schäffler from the Fritz Haber Institute in Berlin and myself. It was a project on thermoelectric materials where we thought, first of all, it's very useful to get organized, because if you don't throw away the data or don't need to search for the data after a while, after a student has left, but also keep in mind that we could reuse the data later on. And we were so convinced about this concept, and we found it so practical that we, at a certain point, and this was in 2014, we opened this repository up to the whole world, so people from all over the world now can upload their electronic structure data, and to some extent also molecular dynamics data, to the central NOMAD repository. Now 2014, this is interesting, this is 2 years or more than 2 years before the term FAIR was coined officially. Nowadays everyone is talking about fair data infrastructures. We just did it, and so far we have collected more than 100 million calculations. And these are calculations from many individual researchers, but also contain raw data from major US-based databases. So that's fine. People can upload the data now, so they are findable. That's the F in the FAIR. So I feel like they're sitting somewhere in the cloud. In reality, it's the Max Planck Data and Computing Center in Garching, actually. But what do I want to point out with this? So we have a central database, and if you have a closer look in there, as mentioned already, we are very organized, because all these calculations, they're sitting in a file structure. So that may be perfectly okay or very useful for people who are experts, so students who perform similar calculations, who want to compare the results, or who want to somehow change probably the input file in order to compute a similar but not exactly the same material. But is this really useful for an engineer or an experimentalist who wants to know what the result of the calculations are? So in fact, not so much, and that's why we have come up with something that makes the data not only machine accessible, but also human accessible. And this is what we call a nomad encyclopedia. So you search for a material, be it in terms of composition or in terms of properties, then you will get a list of materials that fulfill the criteria you have been searching for. And then if you choose one of these materials, then the encyclopedia will tell you what are the structural properties, what is the electronic structure, what's the density of states, what are the phonon properties, what are thermal properties. So whatever people have computed all over the world, we make it visually available. So this is very important if you bring together data from different sources, because then you really can see the wells of this data. But you need something as a prerequisite for this, and this is the I in FAIR, and this is the interoperability. So needless to say that 100 million calculations can't come from a single person, and of course can't come from a single method or a single computer code. And what you see here on the right, this is a snapshot of the Nomad archive at some point in time, which tells you how many different software packages are used in our community. So in fact, Nomad is supporting 40 different codes now. And very important for this was that we fully parse every input and output file. So in other words, we need to interpret all the numbers that you find in these files. And in order to do so, we had to come up with a description of all these items in terms of metadata. And finally, we bring everything into unified file format and units, such that the encyclopedia, but also artificial intelligence tools can operate on the whole data store. So in terms of publishing, we publish data or consider paper like manuscripts that are published, in the sense that every data set is getting a PDI. Everyone can request a digital object identifier. And if you download the data, this works under the CC BY license. I mentioned already that we are, of course, very well embedded internationally. I mentioned the connection with the other databases, but you also can find us in the European Open Science Cloud as a GoFair implementation network, and many other instances. So let me now come to another point, which I think connects very nicely here, because having established a repository, such repository, of course, is also a very good place to host high throughput calculations. Right? So what do I mean with this? I mean, it's very popular now that even if you have not synthesized the material, you just scan possible materials that you can dream up on your computer for the question whether it's useful for one or the other application. So that means you define the properties a material should exhibit, for instance, to be a good solar cell. You would probably need a band gap in the right range. That would be property 1. You would need some or very good light matter interaction. You would need a good transport properties, you name it, right? So you solve for this. Take your favorite properties you would like to see, and then you scan a lot of materials and see whether they pass all these barriers or whether they fall out from the funnel somewhere. So at the end, you probably will see that only a few materials, in this case, it's probably 3, have made it through this funnel. So they fulfill all these properties, all these criteria, but there are thousands others that may not fulfill this criteria. And what we typically do is we close the lid, right? And since we are so happy with these 3 materials, we would take them to heaven, and the rest just goes to hell. So is this okay? Well, of course, that's not trash, right? Because what is useful for one purpose or what is not useful for one purpose may be useful for something completely different. So let's bring this back, let's restore this and keep these candidate materials under consideration for something else. So this actually brings me to the next aspect, and this is the scientific vision, right? So we want to go from data to knowledge, and the scientific vision is, of course, to use all this data to produce something really useful. And I like to draw this, let's say, with this simplified picture that you see here. In fact, we dream of drawing maps at some point in time, which will tell you where in the region of your material space, in terms of composition, in terms of configuration, you may find, for instance, good superconductors or good transparent metals, right? So it's needless to say that this is not a very simple task, and we will need new tools, or to develop new tools in order to do so. So the aim is actually to find out, of course, what is behind these trends and patterns, which you cannot find from a single investigation, but you can draw your conclusions from from big data of material science, right? So the question is, what are these descriptors here that help you to tell apart the materials that may be good for one or the other application? Of course, this won't be a two-dimensional map. It will be much more complicated, but this is, let's say, the goal. It's a longer-term perspective that probably won't be reached in a few months or in a few years. But I think at the end of this process, we should be able to do so. So in order to address how we can do it, I like to talk a little bit about the research that we are doing today and how I envision the research of tomorrow will look like. So what are the research paradigms? Of course, we started very early on, a few hundred years already, with experiments. Nowadays, and what I've shown you so far, in our database, it's just based on theory. So predominantly we solve the Schrödinger equation of quantum mechanics. But now making use of computers and combining the power of computers with theory, we have entered already some decades ago the third research paradigm, and this is computational material science. Computational science in general, but in our case, it's computational material science that, as you see, again, needs new tools like density functional theory, but also molecular dynamics, Monte Carlo simulations. But we can solve them now on the computer, and this allows us to perform so-called computer experiments. And now what many people do on top of this data that are produced by this way, for instance, on top of high-throughput calculations, they try now to use machine learning, or let's say data-driven methodology, in order to extract knowledge. So this is the way we want to go. I've introduced our goals, the final goals to you, and actually in order to reach them, we will definitely need new tools of artificial intelligence. So we need to invoke this fourth paradigm here. Now, but actually, I brought a guest with me, and despite the fact that I just talked about theoretical data at the moment, we shouldn't forget actually what Max Planck told at some point. So Max Planck, who was the initiator of a very famous theorist and the initiator somehow of quantum mechanics, he actually told us that experiment is the only means of knowledge, and everything else is poetry. So obviously theory is poetry, and our computer experiments somehow are poetry. And I actually like to be a poet, but I think I also want to be realistic. And we need to take into account that theory alone definitely will not be good enough in order to learn and in order to predict new materials, but there will also always the interaction between theory and experiment. And in that sense, we're also extending now our data repositories and data infrastructures towards experimental science. And I would like to just address very shortly a few points here that I regard being critical for the future research. So imagine now the FAIRY doesn't only give us all this theoretical data, but we can also have access to all experimental data and, very important, all the data concerning synthesis of materials. So that's great in terms of physics, in terms of science, because of course these data have much more information included compared to just only looking into theory. But at the same time, it also gives us a headache, because you have seen already before, bringing together data from different sources. Just within theory, it's complicated enough because there's so many tools and so many methods and so many approximations that are used and make it hard to operate on all the data at the same time. So now if you think about bringing also experimental data in, this is quite a challenge. And I just exemplify this challenge by one very simple example. And simple means that I just talk about one of the simplest materials you can think of. So it's silver. It's an elemental solid. And also the physical property that I display here, so the optical spectra, is also a very simple quantity. So it's an XY plot, intensity versus energy, right? But now if you compare the different curves that have been obtained over the years by different people operating on different samples, of course, you wouldn't guess that this is the same material, right? So it's not that we're talking about peak positions that differ by milli-electron volt. We really see differences in terms of electron volts here. So actually, to bring data together from these different sources is even a bigger challenge than just looking into theory. So obviously, samples play a crucial role, because a sample is always is always dirty to some extent. And so when do we have a perfect material? When do we have a clean sample? So to know already the quality of sample is crucially important in order to know how we can interpret our experiments. So that's one thing. That's veracity. That's the uncertainty in the data that we have. But in addition to this, we also have to talk about variety, because just look into this case. So here we are talking about the dielectric function. There are several ways, several experimental means of obtaining it, right? So for instance, there's ellipsometry. You can get it from absorption or reflectance spectroscopy. You can even do electron loss spectroscopy in order to get one and the same quantity. Very important is that these quantities are never directly measured, but you always need a transformation step in between. So this again gives you some veracity, because you need probably some approximation, some fitting of data in order to get there. So variety again comes with additional veracity. And on top of this, of course, I need to get back to theory and emphasize that there are many different ways, also theoretical approaches, in order to compute the same thing. So that's fun, but it's a lot of work ahead of us. And this is why I think the I in the FAIR, the interoperability, is really the most crucial aspect when we want to extract knowledge from data. So let me get back just for 2 minutes or so to my trash bins, right? So I've introduced already 2 of them. I have 2 more, right? And this has to do with experiment. Now, what you see here on the right, this is a perfect sample of an aluminum nitride crystal that has been grown by physical vapor transport, right? It's so nice that everyone wants to have it, everyone wants to measure it. And despite this fact that this is a perfect crystal, probably the synthesis or the information about how this crystal has been grown this information may not be published, or at least not be fully published. And there are actually a few aspects related to this. So one reason for this is that, I mean, if you grow the nicest samples, probably you don't want to give away your secret, because you can grow the nicest sample for many, many important labs, right? And this is particularly important if you're talking about industry, right? But there's also another reason, and this is simply sometimes some of the secrets are probably not even known. So sometimes notes are taken, just handwritten notes. Sometimes information is just exchanged during the coffee break of a conference. So, and maybe also the details of the apparatus are not well known. So in essence, but even if you know everything, and even if you publish the information about this, if we only publish success stories, this will lead to bias, because we won't know why, for instance, samples that look like this are not so good as the other sample. So in essence, what I emphasize is that we need to change the publishing culture, in the sense that we also need to publish failures, because only then we could reduce the bias and would enhance the knowledge and understanding about this. And this brings me to my third trash bin, so to say. Don't forget to publish synthesis recipes, even if they don't work. So the other thing also has to do with experiment, and this is what I call the lost metadata. So think about how experiments are formed. So typically, if someone measures something, then people will take down or down some notes about the measurement, or about the growth of the material, or about the setup of the apparatus, right? And then there may be other notes that are taken and probably thrown away right away. But in essence, at the end of the day, or end of a series of measurements, then a paper is published, and everything that has been taken down is basically trashed. So again, this is very, very important aspect, because you may ask the question of how much value data are without being fully annotated. And in fact, we have to see that, in particular in big labs, there's a lot of data that are stored but are not fully annotated. So the question is it really worth keeping them just for the sake of keeping them, because the funding agency tells you to do so, if you can't reuse them in lack of knowledge? So this is my last trash bin, and this is about metadata. So very important that we annotate all the data that we like to keep, that we fully annotate this data in terms of metadata. No, and then here we are. I think since we now have a repository that allows us to keep the data, so we can also host candidate materials from high-throughput calculations, we've come up with a metadata schema already for the theoretical data. This is the Nomad Meta Info. It's a hierarchical schema that describes this theoretical data. We're extending this right now in terms of experiment. And we also have people from the synthesis crystal growth on board in order to make synthesis data available to the community. No, that's fine. It seems that that's all what we need. And since data are a very important raw material of our century, we just can go ahead and turn trash into a gold mine, right? So this is where we go and produce a lot of gold. Well, but wait a moment. So the question is, of course, how would we do this exactly? So I think a very important aspect of this is that we have to understand our data perfectly. And this also means if we bring data together from very different sources, we also need to understand the quality, and we need to understand what the error bars are. So that's why we spend a lot of time at the moment in developing tools that help us assessing methodology and data quality. So I like to show you just one example. So we have implemented in this toolbox so-called similarity measures that will tell you how similar a material to another is. And I exemplify this with the density of states fingerprints that was suggested by Isaev and Cotarolo and this group. In order to assess somehow the similarity of different materials in terms of one quantity. So the idea is, for instance, you have a material and you want to replace this material by something else because your material is toxic and you want to find something that's less toxic. So you need somehow an automated procedure that tells you which materials could be considered for this case. So again, I show you a very simple example, that's gallium arsenide, and you may ask the question, what is most simple to gallium arsenide? So what we find here, by scanning 280,000 materials of the NORMAD encyclopedia, gallium phosphide. So gallium phosphide has a similarity coefficient of 0.83, and I need to explain what this is. Actually, it can go between a range between 0, which means completely dissimilar, and 1, which means identical. And you can guess already where this dissimilarity comes from, or the deviation from 1. It's simply this difference here in the conduction band. But in the terms of valence band, they're very similar. So of course you could argue, well, I could have told you this, that gallium phosphide is similar to gallium arsenide, right? But probably you wouldn't have guessed that this material is also similar in terms of the valence band structure. It has a smaller similarity coefficient because we have more differences here in the conduction part, but very importantly here in the valence region, right? So I think this is a very good scientific tool. So it's not only infrastructure, but scientific tool. But we use the similarity coefficient in order to assess data quality. So, and I would like to spend some time on this in order to exemplify. So again, a very simple example, I take bulk silicon in diamond structure, space group 227. And if you look up the NORMAD repository, you find 2,625 calculations just of the same material. And of course, you may ask the question, do all these calculations give the same result? So let's have a look into how they are distributed. Obviously, many different codes have been used. 1,500 with FHI aims, 500 is fast, 300 octopus, and so on and so forth. So how similar are the results? I'll show you one example first, and this is one example where we use the same code. It's both exciting calculations, but we vary the methodology. So one is the local density approximation that's shown in yellow, and the other, this is the GW approach of many-body perturbation theory. So obviously the similarity coefficient is not bad, but also not too good. And yeah, you see, of course, that GW shifts the conduction bands to higher energies. And that's why we have differences between these two curves. I mean, again, you could argue, I could have guessed this because I know what GW is doing, but here we have a means that somehow scans hundreds, thousands, and millions of calculations and finds it out by itself. Huh? So, but it's a way in order to assess the impact of methodology on the results. And as a second example, I stay with the same method. So these are both GGA calculations in the PBE parameterization, but now these are calculations performed by two different codes. Now they're more similar than the example on the right side because it's the same method, but still there are differences, and you see the differences becoming more pronounced if you go to lower energies. So in that sense, you could argue, fine, these are calculations. They differ mainly in terms of the potential because VASP is a pseudo-potential and FHIMs is an all-electron calculation. So of course you can argue you could also investigate the parameters, computational parameters, and so on and so forth. So let's do two examples just to tell you that we can use such a tool to automatically assess the impact of one or the other aspect, approximation parameters or whatnot. And this, in fact, this last example that brings me back to a paper that was published a few years ago, exactly asking the question, if we have given a material and given a crystal structure, if we take two codes, do they really produce the same results? And I like to show you, walking very slowly through this example, since I think it was a really important step, initial step in order to talk about data quality and reproducibility of data, of results. So it was initiated by Stéphane Cottenier and largely also carried out by Kurt, his student. From my group, there were two guys, Andres and Sven, involved in this. So what is it? I think in short, people simply call it most of the delta test. And the delta means the following. You have an energy versus volume curve. So you pick one code and you compute the energy versus volume. Then you pick another code and do the same. And then you evaluate a quality factor. And this quality factor tells you not only what's the difference in the minimum of this curve, but tells you also what's the difference over the whole range. So, and this is the famous delta factor. So if you now go to this web page that was set up by Stéphane and Kurt, then you can choose a code that you like. Of course, we started with exciting because this is what we developed. And then you see from this delta value how different other codes are performing, right? And then you see that I would say at least 10 different codes, they distinguish or they differ only by 0.5 milli-electron volt by atom. So this is an extremely small quantity. And in that sense, you can ask, well, lessons learned, obviously all the codes give the same result, right? Actually, I need to ask if there's a question because I can't see.
Yeah, actually, I mean, I was waiting to finish this example because there is a question by Mevari Kalwani who says, all this is good, but can you tell us about some success stories about the use of Nomad? So I don't know if you consider this a success story or do they will come later or you want to comment about them now?
Yeah, probably I can comment on this later because this is an overall, maybe a very specific, no, it's not a specific thing, it's a very global question to how you can get results out of data, right?
Yeah, okay.
Yeah, but you can interrupt me actually if you like, because I don't see how to say that.
Yeah, no, yes.
Okay, so that means that all the codes give the same results, or more or less the same results. However, we need to take into account that there are that this is an average, and this is an average on 71 elemental solids. So the sum of these error bars are much smaller, but some of them are much larger. So for instance, chromium here, if you compare, for instance, exciting with quantum espresso. Now you could argue, of course.
Sorry, yeah, Claudia, because maybe this is just the example you just described about delta, because Nicola Marini asked, the volume curve is good for cubic materials, but what about lower symmetries?
Yeah, actually, this is a point that I just want to make. I think this delta test was a great start, but it's only a start because you have to think about that the elemental solids are very forgiving. So there are also total energies are very forgiving. And if you go to other materials, and I have this on my next slide, so to say, if you go to other materials and other quantities, we will see that there are much bigger discrepancies. So I think this was very nice, but actually we also have to say it took years until to get this precision and this agreement. And I think it will take another few years in order to get this agreement for more complex examples. You see already here you have discrepancies, more stronger discrepancies for single elements. And now you could say, okay, maybe chromium has an issue with the pseudopotential, such that an all electron and the pseudopotential don't agree very, very nicely. Actually, this heat map, so to say, tells you the darker the color, the bigger the discrepancies. So if you now take, for instance, a comparison between two codes which implement the same method, then it looks much calmer, so to say, because still you have some discrepancies that are bigger than this target value of 0.5 millielectron volt, but the differences are much smaller if you use the same methodology. So, and as I pointed out already, so this was exciting versus V2K. Other systems and other quantities may be much more critical and needs to further develop. And actually, I would like to zoom into one example here, and this is iron, where you see the agreement is very good, also with quantum espresso. It's just about 1, this delta factor here. However, if you go away from just evaluating the energy, but look into the properties, the picture is a completely different one. So let me explain you. What we show here is for BCC iron, the bulk modulus versus the lattice parameter. And all these red dots here are results from this delta test. And also all the yellow triangles are results from the delta test. I marked them separately because these are all electron LAPW calculations. So, and there are 3 lessons that we learned from here. One is that the spread in properties is much bigger than the spread in energies. You see here the lattice parameter has a change of more than 1–2%, right? And also the bulk modulus differs quite a bit. And what we also learn is that if you look at the experimental values, we never should draw a conclusion on the agreement with experiment, because actually the best value that we have, this is the crossing point of the green lines, this yellow triangle is farthest away from experiment. So, and we also learned that we cannot draw our conclusions here because the motivation for the delta test was to distinguish between the numerical precision of a calculation and the accuracy of a functional. And now if you zoom in here, and here I've added more calculations with different functionals that are highly precise, then we see that the spread of the delta test results covers 4 or 5 functionals, right? And so we learned from it this PBE is not the best functional, but we also learn that the precision that we have reached here is not good enough in order to access properties.
Claudia.
On the other hand, since we have a tool now how to evaluate the precision of a calculation, we can now really also evaluate the accuracy of a method, right? And what I show you here is again such a heat map of the periodic table. And the color here tells you what the impact, for instance, of spin-orbit coupling is on the energy. Right? So,
Claudia, sorry, just before you move on, there is a question by Kurt Kremer about the similarity measures. He says, assuming that there is no problem with the calculation itself, to what extent are physical arguments used to define a similarity measure? Because this could lead to rather different results.
Yeah, actually there are several similarity measures, and I think this is one that somehow measures the density of states. And I show on purpose actually very different things, so also the delta test, because different quantities need different measures. And I also have to say that this similarity, I mean, this is a critical issue, and just I think relying on one similarity measure is not good enough. We have to look into different ones. So in that sense, we have implemented very many different such descriptors, if you like, also the SOAP descriptor and all kinds of things, just to see how sensitive a property is to a certain measure or to a certain descriptor. Yeah? So the similarity measure of the density of states is something which I think it's easy to understand. That's why I think it's a nice example to show. But it's definitely not something we could fully rely on when assessing other properties.
Okay.
So in that sense, this delta value is also a similarity measure, and it tells in this case how similar materials with and without spin-orbit coupling is. And what we learn here, for instance, if you want to run a scandium calculation, you can safely ignore spin-orbit coupling and take a code that hasn't implemented it. But if you want to treat polonium or bismuth or mercury or gold, you better do so, because you see polonium is 40 times the threshold that we had before in the precision we have been asking for. Now, of course, this is, so to say, the energetics here, but you also see that it has an impact of the properties. So again, what I show here is the volume. And so everything that is in red means that upon spin-orbit coupling volume increases, everything that is in blue indicates that the volume shrinks by spin-orbit coupling. And you see here, this can be as much as 6% of the volume or 7% of the volume. And this again would, of course, also change the electronic structure of the system. So, having talked about data quality, I would like to finally come to the major aim of the whole thing, because in order to extract knowledge from data, we need to come up with artificial intelligence and machine learning tools that help us to do so. And well, you may argue that everything is happening already, so is there anything that needs to be done left? And in fact, how hot the field is shows me the March meeting, the APS March meeting that I've attended, I don't know, 1 or 2 weeks ago. And I just looked up the program and scanned it for these buzzwords here. So data science, machine learning, deep learning, artificial intelligence. And this is what I found. So, and this is not the number of contributions to the conference, but this is number of sessions. So there are 51 sessions that were dedicated just to data science. Right? And then you really may argue that probably everything is known already. We know already how to deal with all these questions and problems that we have. Now, I think it's great what's happening right now. I also want to mention or to recall that we are not necessarily reinventing the wheel. So there are many areas that have come up with data-driven approaches already. In particular, cheminformatics, for instance, is a very old field, and machine learning in chemistry obviously works very well. And but there's also, I mean, for instance, social media, I mean, take Google and Facebook and so on, they have contributed a lot to our tools that we have in hands right now. And I mean, you name it, starting from machine learning tools, random forests, or kernel-rich regression. We can learn from data processing like compressed sensing and so on. So I think this is very important, that we can make use of the tools, and obviously the community is making use of these tools, but we also have to keep an eye on the fact that we cannot take these tools just from shelf, but we have to put also domain-specific knowledge into our research in order to get the precision and the accuracy that we finally want to have in order to have predictive power. And this, in fact, brings me to one of the last points that I want to make. So I now go to the research of tomorrow, and I come back to the transparency that I've shown you before. This is our aim to find materials, or to predict materials that may be useful for one or the other application. So obviously we need to assess, by having data tools, we need to assess trends and patterns. And I would like to address two important things that we need in order to reach our goal. And one, of course, is the tools. This is what I've just been talking about. very important for me is that these tools have predictive power. And predictive power means that they go beyond interpolation. And this is the reason why I said we shouldn't rely on taking just tools that have been developed in a different context and just apply it, because if you do so, then probably we always stay within one box. That means we can interpolate very well, and this is probably why cheminformatics is so successful. But if we want to consider materials that has been, let's say, considered for transparent metals, and you keep inside these transparent metals, you will never somehow get out of the box, and you will never predict something that's exceptional. And with exceptional, I mean, I want to find a pearl, right? I want to find something that is better than what we have in hands right now, just with just a little bit progress, right? So in that sense, and this is what I mentioned before, we should also keep all candidate materials in mind, not just for the purpose they have been created for instance, for finding a transparent metal, but also for any other purpose. So tools with predictive power is very important. And in that sense, I think it's also very important that we publish our tools. So it's not only about publishing data, but also publishing tools such that people can reuse them, change the parameters, let them act on their own data. And in that sense, to fully document and publish machine learning artificial intelligence models is very, very important. So could be, for instance, like a supplementary material to a publication. The other point is we need not only big data, we need the right data. And with the right data, I mean, they need to carry the relevant information, right? So in other words, if we want to find the pearl, it's not good enough to increase the number of data that helps you to describe the water around and the sand on the shore better, but we need to have the data that keep the relevant information on the pearl. And the other thing is, of course, and this is what I talked about quite a bit, is that this data need to be, call it clean, so they need to be well described, well characterized, and of high quality. So since, yeah, I'm coming to the end actually, but since I've been asked already, so are there success stories, right? So I like to show you just some simple examples of such maps that you can find in the Nomad Analytics Toolkit. And of course, these are not yet the big final answers, but these are, let's say, first steps. They are prototypes for telling you, for instance, how you can predict crystal structures, right? So how can you tell apart, for instance, different phases, or so you find several examples of this here, or you can tell apart metals from insulators or topological insulators from trivial insulators. So all these examples exist already, and you can play with this because also the tools, not only the data, are open. And so I would like to spend probably the last 1 minute or so or two by just quickly showing you how this works, how we're doing this. And I picked for this a very famous problem. It's called the Phillips van Vechten problem, because Phillips and van Vechten have been working on this already in the late 60s or 70s of the last century. The question is, if you give me two atoms, A and B, that would find an octet, what would the crystal structure be, right? And you would like to predict this from entities that don't involve the crystals themselves. So in other words, you would like to tell apart rock salt from zinc blende structures, like here. Huh? So to show you how we do it is that we build a feature space. So we select properties that are only the properties of the atoms, like the radius, atomic radius, or the electron affinity or ionization potential, or band gap, or things like that. And then we build a feature space by nonlinear combinations of these, what we call primary features. And this could be 10,000, 100,000, or millions. And then we apply a compressed sensing method in order to learn the relationship between the real property that has been calculated, could also be used for measured data, and the descriptors and our feature space, right? By minimizing this expression, and its compressed sensing is realized here by this L1 model for the experts. So, and this is the result. That's my final slide. There you can see that already from a two-dimensional descriptor, just 2 parameters, you can tell apart everything that is crystallizing in zinc blende from everything that's crystallizing in rock salt. So to tell you what the color code means is that we've computed the total energy difference between these 2 different phases, and where it's in favor of rock salt, it will be blue, and where it's in favor of zinc blende, it will be red. And then you see this descriptor, this can distinguish both of them very well. And all these points that are in green, these are those where the total energy difference is so small that the system has a hard time to distinguish or to decide which what it wants to be. And all of them are along the separation line, right? So, and all this is just predicted from the properties of the few of the single atoms. Okay, that brings me to the end. I just wrap up here by this slide by just reminding you what very important aspects are that bring you from, let's say, data to knowledge. And with this, I'd like to thank you for your attention.
Okay, I'm here. So thank you very much, Claudia, for this nice and thorough presentation. We enter now in the Q&A. As I mentioned at the beginning, if you want to ask a question, just use the Q&A panel that you have in your Zoom window, and it's enough that you indicate that you want to ask a question, and then we will give you access. So you will have to unmute yourself, and then you can ask the question. There was actually a question that was made towards the end of your presentation, but because you weren't making these examples, I just prefer to wait. I think at this point, maybe it's better if Sandeep can ask the question live and explain what he wants to ask related to this kernel ridge regression. Sandeep, you need to unmute yourself and then you can ask the question.
Maybe I...
So, yeah. Hi. Yes.
This is Sandeep, and thank you very much for nice talk. I'm just wondering about the machine learning model, means kernel is a regression. So let's say we have a small database. Let's say we have 5,000 or 6,000, because machine learning works well if you have big database. So let's say if we have the small database, can we use this kernel ridge regressions model to predict some good properties? I'm just wondering if you can say something about it.
Yeah. I mean, that's clear that some of these methods are more data hungry than others. But I would not just argue with the number of data. As I really pointed out at the end, we really should also care about the quality of the data. So if we have enough data that carry enough information, then sometimes you get along with a very small data set. Sometimes, as I said, if you just increase the knowledge about sand and water, probably you cannot predict the pearl, right? So it depends very much on the problem and depends very much on the quality of data.
Okay, let's say we have the band gap database and we use hybrid functions. So we have few material, let's say 5,000 with the help of hybrid functions. So then let's say we have the database for formation energy and band gap, and we have only 5,000 material database. So in this case, can we use this KKR method, KKR model to predict because hybrid calculation is always expensive, so we cannot generate more data. This is the reason I'm just wondering, means suppose if this type of data we have and it's in a small database. So I'm just wondering, means
I don't think that 5,000 data is necessarily small. I mean, as I said, it depends what you want to predict. and how good the quality or the variety of this data is, and of course also of the method. If you use a kernel, then of course it also depends on the kernel that you're applying. I think what is important is that you always assess the quality of the model, and in that sense, if you do a cross-validation of your results, you will learn whether your model is good enough or not. Then you can rule out some models, and you also can see if what happens if you leave out 10% of the data or 50% of the data, how the model changes. And the cross-validation is a very good measure of how predictive and how good your model is. Because, but of course, you can also look at the mean square error, which is also a good measure, but it only gives you an idea about the interpolation of data, whereas the cross-validation would give you an idea how predictive your model would be. Both is very important, I think, for assessment of your model.
Thank you very much, Professor Claudia. Thank you.
Thank you. So there is then next question by Fabio Affinito. So Fabio, can you unmute yourself?
Yes, hello. My question is a request for a comment on two different aspects. One is when talking about remote data. You claimed at the beginning of the talk that sometimes we are talking about terabytes of data that are located maybe very, very far apart from the place in which you want to perform a data analysis, for example. So how much you think the infrastructure will be relevant for this kind of operation? So how much the data locality will be important for this kind of things?
Yeah, I think this is a very good point. Infrastructure is very important. That's why I think there's a lot of initiatives also in different countries to build infrastructures. So far in Nomad, we were not hit by the amount of data, by the volume. So far, I think the amount is still in a size where everything can be uploaded to a central repository. But now working together with experimentalists, we are working on a distributed data infrastructure such that the intense or the large data stay at the place where they have been created, but will be processed according to certain schemes that are the same for everyone. So metadata standards and so will be the same. And only the most important information or the metadata will then be centrally available, such that if you want to use the data, you still have access to them, but you don't need necessarily to bring together all the data from all over the world, from all the electron microscopes into one place. I think this is hopeless and also not needed. And of course, in information technology, in informatics, there's also one motivation is to bring not data to the code, but code to the data, such that we develop also distributed tools that operate on data locally and then just bring the results together. So these are things of actual research, I would say, but they will be very important for the future because it won't be possible to have all the data in one place.
Mm-hmm. Okay. Thank you.
If I can say just one thing, yes, probably I think that in the past we can learn from the experience, for example, in other fields, for example, in astrophysics research, where the analysis of data is something that has a long history, because you have tons of data that should look for very, very small variation, and that cannot be performed in a different way than with the remote analysis. So probably some tools could be exported also to different domains, and probably this is something that will be very challenging for the future of this kind of initiatives.
Sure, yeah, I think the tools of processing data and storing and compressing data, I think this is what many research areas have in common. I think an advantage of this, let's say, CERN or big data stores is that they have very data of the same kind. I think what really hits material science is that we have very heterogeneous data, many different instruments, many different, resolution, many different quantities, many different levels of accuracy and precision. So this is the main challenge, I think, this interoperability that we are facing. Everything else is probably easier to control.
Okay, thank you. There is then next question by Mevarek Alwani.
Yes, hello. Hi, Claudia. Hi, how are you?
Thank you.
I have a question concerning portability. I mean, you spoke about this science paper that you did 2 years ago, I think, about comparing all these codes and properties and so on. I know that actually it took a lot of time actually to adjust all these to the potential, to get agreement and so on.
Yeah.
Because at the beginning results were not very good. And now my concern is actually when people put data on a database, I mean, where actually pseudo potential were maybe completely wrong, results can be off by a lot.
Yeah.
How can you rely on these data that is you put in your, let's say, Nomad, actually predict something out of this? Because it seems to me that the errors could be really huge, so that the database will be useless somehow.
Yeah. Well, no, so no, I mean, I agree. That's why it's so important to describe the data properly, that we know what people have done, that every parameter is known, right? But this is also the reason why I emphasize so much the data quality.
Sorry, it's not actually the calculation is wrong by itself. I mean, the quality of the pseudo potential, or let's say the potential used is completely not, especially when the system is very complex. Let's say you have 40, 50, 60 atoms per unit cells, and things get really off.
No, I fully agree, actually, but I also want to emphasize, I think no calculation is wrong per se. We have the input and the output file, and we know what the code is, so every calculation can be redone, and so it's valid in the sense. But again, I put so much emphasis on the data analysis, so not only the analytics and machine learning, but the analysis of data in order to understand the data quality. And by, for instance, I mean, the similarity measure was a very simple thing, but actually it could already see the difference between LDA and GW. And by that, or by similar means, we can evaluate what the impact of a certain pseudo potential is, what the impact of certain parameters are, what the impact of certain functional is. And this can also be done materials resolved. So for instance, we know that LDA is good enough for a metal, or we could figure out that GW is needed for semiconductors. These are things that should come out automatically if we develop tools that are suitable for detecting these differences.
I can actually understand it the other way around. Actually, for a person making a calculation, it could use a database where actually it's with the artificial intelligence, in order that actually shows how wrong is pseudo potential, for example.
Definitely,
Performance. It's actually get it backwards instead of actually using the data to predict something, actually showing that how people will calculate actually.
Actually, we are working on a recommender system. This is a big project with the informatics people here in Berlin. And this recommender system that should tell you, given I want to compute a certain material or a certain property, could you recommend me what methodology, what potential, what functional, what parameters to use in order to get reasonable results?
Yes. Yes.
That would be something that would be the outcome of such automated analysis.
Absolutely. I mean, I can see it backwards working.
But again, so if you go to the repository and then see what other people have done, then you can compare your own results and see whether this is the same or whether it's different. So you can also do manual inspection before do it automatic.
Yeah. Okay. Thank you. Thank you.
Okay. Thank you very much. There is also then a comment by Gianmarco Rigagnese.
Yeah, it's actually a comment to Mebarek's comment. So my point was just to say that, I mean, even experiment, as Claudia has shown, there can be different results. She showed the case of silver, where the difference, the measurements were different. And so one way to handle that in machine learning is use what is called the multifidelity. There's a paper on the archive by the group of Shuiping Ong, where they try to use that. You know, for instance, they have 600 data points from experiment for the band gap, 6,000 data points for the from HSE calculation, and 60,000 calculation for PBE. And they know that each of them has a different accuracy, and they try to exploit that in order to make a better prediction for the experimental gap.
Okay. Thank you. So I don't see any further questions, but so thank you very much, Claudia, for the talk and for all this type of discussion. And we will then now move to the second speaker of this first part of today's event. It's Aram Hospital. He will be talking about BioExcel C19, a database of COVID-19 related molecular dynamic trajectories. So please, Aram, now the floor is yours.
Okay. Hello. Let me try to share the screen. Okay, can you see my screen?
Yes. Yeah.
Okay. So let me start thanking the organizers for selecting our poster to be upgraded to this short talk. Thank you for that. And I have to say that, when I was preparing the poster, I thought that I wasn't quite sure about our project was fitting exactly the topic of this webinar session. Then when I started preparing when the poster got accepted and upgraded, I started preparing the presentation. Then I realized that maybe it was fitting better than I was expecting at the beginning. And then after this beautiful presentation that Professor Draxel has just given us, I'm quite sure that it's fitting, even if we are not using machine learning or AI in our data. But I hope that you will agree with me at the end of the presentation. Okay, so I'm going to talk about the database of COVID-19 related molecular dynamics trajectories that we are developing within the framework of the BioExcel Center of Excellence. This is the approach that we are following, the approach of data-driven science, in our case, but data-driven approach at the end, in a general way, applied to biomolecular simulations data. So we started with a set of data, collection of data. In our case, that means that we are dealing with molecular dynamics data, and I will introduce a little bit that in the next slide for the ones that are not familiar with this type of data. Then what we are doing is in the step of this data-driven approach pipeline. What we are doing is to organize this data. That means that we are collecting all the data together. We are looking at all the metadata and putting all in the same page. And I will give you examples on that. And after that, we are analyzing, we are extracting useful information, meaningful information from these massive amounts of data. After that, what we are doing is to collect everything in one single database and associated web server. And I will show you examples of this. And we are opening everything to the scientific community so that then the scientific community can act on this data and add value to all of these data. The biomolecular simulation field, basically in the particular field of molecular dynamic simulation, which is the one that we are working with, we start with a static picture of a macromolecule, three-dimensional macromolecule. In this case, this is a protein. That means that we have basically atoms, atomic coordinates, X, Y, and Z in 3D. We typically use structures that we can download from this standard and popular database, which is called Protein Data Bank, where all the experimentally solved structures are uploaded. Then we apply molecular dynamics tools, which are computationally expensive. That's why we usually use supercomputers to run this type of calculations. we extract the motions of these structures. Here we have a picture. Here we have how the protein or the macromolecule is moving. That means we have dynamics and flexibility properties. And after that, what we are doing is, of course, not just use one particular MD, but many different MDs and a collection of MD simulations. In the particular case that I'm going to talk about today, we are working with a collection of COVID-19 related molecular dynamics simulations. In terms of data, what that means is that we start with a static picture which have the size of megabytes. Then we run the molecular dynamics tools, which is computationally expensive. So maybe we should spend like 1 week for just one molecular dynamics simulation, and we end up having a trajectory, molecular dynamics trajectory that it's in this case in the size of tens or hundreds of gigabytes, even reaching the terabyte nowadays. And when we talked about the collection of MD simulations, then we have hundreds of terabytes and even petabytes, and that's the amount of data that we are dealing with in this kind of projects. Okay, a little bit of a story behind this database on web server. Actually, all started like 10, 11 years ago in our group. We have a good expertise, I would say now, on databases of molecular dynamics simulations. This one in 2010, we managed to produce a database of almost 2,000 different MD simulations, protein MD simulations in this molecular dynamics extended library. In 2015, we did the same with new technology and now applied to just nucleic acids molecular dynamics trajectories. And then 1 year after that, we were lucky to be involved in this BioExcel Center of Excellence H2020 European funded project, which is a central hub for biomolecular modeling and simulations. And within this project, and after the appearance of the COVID-19 pandemics last year, as all of you know, we started different research focused on this COVID-19 disease. And one of these projects were exactly this database and web server, associated web server to share these molecular dynamics trajectories related to COVID-19. The seed of the project actually was this hub, which is, again, a web server that we developed together, BioExcel Center of Excellence and the Molecular Science Software Institute in the States. This COVID-19 Molecular Structure and Therapeutics Hub, it's, as you can see here, it's a community-driven data repository, which contains COVID-19 related structures, models, therapeutics, and simulations. And we are really interested on these simulations, and this is just an example. These simulations that we have in this server are coming from the most important groups in the field, the short research, folding at home, Zhang, so Fricken, for example. So the most important ones. And in this example, you can see the information that it contains, that this server contains, metadata about the trajectory, force field, etc. And the most important thing is this get trajectory that you can see here. I hope that you can see it. This is a link where if you click it, you can download the trajectory. This is all we have. So this is really nice. Many different trajectories, all related to COVID-19, separated in the different molecular units, as I will tell you in a minute. But what you have is a link, and you need to, if you are interested in that, you need to download each of these trajectories and treat the trajectories in your own computer if you want to start digging in the information that this data contains. And that's why we start this data-driven approach to first collect the data in one single repository, but not just a link to the trajectory, but the whole trajectory, information on the different atoms, metadata, and etc. So the first part of our approach was to collect and organize. And for that, we used an infrastructure that we have been updating during all these years with all the expertise on the different MD databases that we have developed in the group. And you can see a summary of that in this review that we published last year. But basically, we start with a database where we store all the trajectory coordinates. That means X, Y, and Z coordinates, universal X, Y, and Z for all the atoms, for all the frames, for all the molecular dynamics trajectories. That's a massive amount of data in NoSQL new technology databases. And also the analysis and all the metadata also in this kind of databases. Then we have a backend server with a RESTful API to efficiently retrieve all this information. And then we have a front end, which is the one that through a web-based graphical user interface is offering all of this information to our client, which in this case is our scientists. We are doing that with all this new technology, but and you have a link here in case you want to take a look at the web server. So organizing this means that what we have is a list of molecular dynamic simulations that we can browse and we can search different units, molecular units of the related to the COVID-19 or SARS-CoV-2, as maybe you can recognize the receptor binding domain, the angiotensin converting enzyme 2, which is the human one. RBD is the one that is recognizing these ACE2, so this is the link, the complex, which is basically this one, that is giving the infectiveness to the virus. So a lot of different units really important for the COVID-19 disease studies. All of these entries are have a unique ID, and here it comes the FAIR identifier, so you can identify the trajectory with just one unique ID. And then of course, you can take a look at the graphical representation of the trajectory and all the metadata related to the structure in this case and the trajectory in this other case. So we have everything organized in one single place, all the trajectory in the database and all the metadata associated to that. Now, the second step of the data-driven approach is the analysis. Extract useful information from all these data that we have already collected. And for that, we are using a supercomputer in the BSC, Barcelona Supercomputing Center premises, which is called Starlight, which is a supercomputer combined with 3 different institutes here in Barcelona. The molecular dynamic simulations are really computationally expensive. The analyses are mostly also expensive. That's why we need to use a kind of a supercomputer like that. And for the analysis workflows, we are using another library that we are developing in the BioAccel Center of Excellence, which is called BioAccel Building Blocks. I'm not going into details about that, but basically what this library is offering us is interoperability between the different tools that we are using every day in our work to analyze molecular dynamics data. And this is a set of Python wrappers that we can use together to build workflows. And in this case, what we are doing is to build a reproducible workflow to extract a collection of analyses, and then we upload all the analysis to the database, and the server is offering all these analyses in an interactive and graphical way to the scientific community. These are examples of the first and easier analysis, which we call it quality control, and it's a way to see if the trajectory that we have uploaded in the database, for example, the structure is deviating a lot from the starting point. If you remember the slide of the static picture and then the dynamic picture. So this is a static one. We start from this one and we are differing. The structure is differing along the trajectory, and we can see if it is stable during the trajectory. We can also see how much the shape of the trajectory is modifying along the trajectory. We can also see if the fluctuation of some of the atoms are too high, or we can also see global motion with this principal component analysis of the protein in this case. Those are our quality controls, but then we can move to more complicated analysis, which are the interface analysis in this case for the macromolecules that contains not just one unit, but 2 units, such as the interface between the complex between the receptor binding domain and the angiotensin converting enzyme, or the spike, the well-known spike protein, which is a trimer. In these interfaces, which is the region where the 2 units are connecting one to the other, we can, for example, extract information such as the distance between all the different residues. In this case, if we click in one of these cells here, red ones means a shorter distance. We can see here, and we also can play and see how these residues are moving along the trajectory and see when they are interacting and when they are not interacting in the interface of this particular complex. Just as an example of the added value that we can extract from this graphical analysis, which are already pre-computed, and you can take a look at the web server. I will show you an example of an energetic analysis between, in this case, we are talking about this human angiotensin converting enzyme 2, and this is a DSHO research trajectory where they were trying different FDA-approved drugs. This is the drug that it's embedded inside the human ACE2, and this is the energetic electrostatic and van der Waals interactions between the protein surrounding the residues surrounding this ligand and the atoms in the ligand. What we can see is that there is one particular residue, this aspartic one, which has an atom, not the atom, the residue, which has an energy which is -4, which is really good in comparison with the other. If we click here, we can see why this residue has a so big energy, because there is a fantastic hydrogen bonds between the residue of the protein and the one of the atoms of the ligand. And if we go to another analysis, which is a hydrogen bond analysis, we can see that this particular residues here, this aspartic acid, is making hydrogen bonds first with one oxygen, then with the other oxygen, which because they are swapping. And you can see here when there is white here, there is blue here, which means that the hydrogen bond exists. And when it's white, it means that hydrogen bond is not existing. And how this hydrogen bond is dividing between the two oxygens of this aspartic. This is just an example of what the information that you can extract from this database, from the analysis that the database contain. The database, of course, has an important part here, and it is the programmatic access through a REST API. That means that basically there is a lot of information about this in this Swagger documentation, but basically what we can do is something like this, which is programmatically extract a topology and trajectory with just these lines, these really easy lines, and you can reproduce, you can extract the information of the trajectory and use this information in your own computer. Of course, the good thing about this is that you can play with the different frames. Let's say I'm interested in the frame from 1 to the 2000 frame. I hope that you can see it. And one every 2 frames, this will generate this kind of a trajectory, reduced trajectory that you can analyze in your own machine. And we can do exactly the same with all the different analyses, not just the trajectories, but this is a programmatic access to all the database that we are producing. As a summary, we have generated a database of COVID-19 related trajectories, which is prepared for hundreds of terabytes of data. We have the analysis workflow that now is running in the BSC supercomputers in a reproducible way. That means that we can port it to different supercomputers with all the analysis that then we are uploading to the database. And we have generated an associated web server with graphical and interactive analysis representation. I would suggest, if you can take a look, click on the link and try to play a little bit with the interactiveness of the web server. The next steps that we have is to integrate new analysis, of course, and this is something that we are doing. We are currently doing with community feedback. So all the authors of the simulations, we contact directly them and we ask them, what is the particular feature that you think it's important for us to implement in the web server, and we are doing that. We want to upload new trajectories, of course, improve the user experience and documentation of the website, implement an advanced search, and run meta-analysis, which means analysis not on just one trajectory, but analysis which can be obtained from different trajectories at the same time with this programmatic access to the database. With that, I would like to thank first our institute, IRB, and the BSC to let us work with the supercomputers there. The 2 projects which allow us to build all of this infrastructure, the human brain and the BioXcel, and Danny and Aurélien, which are the guys implementing all of this, and Modesto, which is who is coordinating all the work. And with that, I would like to thank you for your attention. And just now, I know that there is a query answer session, But then I will also be in the poster session, poster number 2 in Gather, so we can keep the conversation if you are interested in this project there. Thank you very much.
Okay, Adam, thank you very much. Now we have the section for the questions and the discussion. I remind you that you can simply indicate in the Q&A section of your Zoom window that you want to make a question, then I will give you the word. So the first question is by Gianmarco Rigagnese. So Gianmarco, please.
Yeah, it's actually a comment. Thank you very much, Adam, for this very nice talk. As you may know, so I mean, as Claudia was pointing, there's many different databases of materials properties. And we also, each of those has its own API. And so we've been developing a common API between all of these. And maybe you know that SECAM is funding a postdoc now for, maybe he's attending actually to this meeting. He's funding a postdoc to work in direction of opening this API, which is called Optimate, to molecular dynamics. And so the work that you have done is really important to us. And so I would like to invite you to a workshop that we are having at SECAM in June. So I'll send you an email and maybe I'll go to your poster later on. Thank you very much.
I would be happy to be there. Thank you.
Okay, thank you very much. So Paolo Carloni also has a question. Paolo, if you can unmute yourself.
Adam, great talk. Could you give a perspective on a more general basis, namely, we will do our simulations in the future, our R&D simulations in the future, all on platforms like the one we have here in Munich, the Phoenix, or the ones that you specify. So is this really the way to go, or you think this will be something that is developing but not really somehow making a paradigm shift in the way we run our simulations? What are your thoughts about that?
You mean in the sense of sharing the simulations instead of running them again, or you mean in running them in different infrastructures?
Yeah, both eventually. So that for the moment, most of our calculations are local, as you know, and I was wondering whether you think this is something that will involve basically all of us from our community, or is something that will stay on the side. So what are your thoughts about this?
I think we should work as a community, and you know, in BioExcel we are working a lot on that and trying to do that. I think that it makes no sense to keep working on running molecular dynamics simulations without having different databases, or at least one database sharing all this information, which is already there and is already computed. You don't need to recompute it again. It's complicated, but there are different initiatives that are now, you know, starting to come out. For example, GPCR-MD is a fantastic initiative also here in Barcelona about GPCR molecular dynamics and how to share this information and analysis. We are now working on this one, and we are really happy on what we are doing about running the simulations. I think that there's no way to run these kind of simulations that we now want, which are microseconds and beyond, without a kind of infrastructure like the one that ICI Phoenix, for example, is providing. There's some of the simulations, the shorter ones or the replica ones, that maybe we can do it within a distributed interface, such as the cloud infrastructures that ICI Phoenix is also providing. But for these very long simulations, we still need to use HPC supercomputers. The thing is how easy it would be to reach these resources in the future. And I think that we should work a little bit more on that, especially for the smaller groups which they don't have access to these resources. But this is another discussion.
Okay, thank you very much. Then now there is a question by Kurt Kremer. So Kurt, you mute yourself.
Yeah, thank you very much for the nice talk. I first would like to very shortly comment on the question of Paolo. I think it's kind of obvious that more or less complete software systems will be available to many people, and many more people will use it, which has positive and negative aspects when one thinks of the knowledge of the people who then will use these tools. Another aspect which I think we have to think about in the future is, of course, the energy consumption of the computers we are using. when you see what is coming up with, on the exascale, in the exascale field, we are talking about an order of 10 increase in electricity we need. That is something we have to discuss or think about. But I have a different question, a very elementary question to the beginning of your talk. You mentioned this increase of amounts of data which you have to store when you store these trajectories. Your calculations are based on all atom simulations, and that means you have a protein complex and all the solvent in the surrounding. Can you say something about the ratio of solvent molecules to atoms in the protein, which you have to store, and do you have some compression or reduction methods to reduce the size of the data sets?
That's a fantastic question. What we are doing in this particular project is to just, I would say, get rid of the solvent. So that means that we are analyzing all the solute, just the solute, not the solvent. But it's a question that it's on the table for years now. How could we, especially now that we have big infrastructures, big HPC centers, databases that we now can start to think about not just saving or storing the solute coordinates and analysis, but also at least part of the solvent, which is the one surrounding the protein, which for us is really important. But so far we have been not able to do that in the kind of infrastructures that we have. But this is a really nice question. And the thing is, I think that what we are going to do in the next year is to start saving not just the solute, but also the solute with part of the solvent, the one that is surrounding, and then after that, if we can, we will store everything.
So don't you have to reintroduce at least locally solvent for some of your analysis runs?
Not for the analysis that we have.
Okay. Thanks.
Building on this question, so the challenge to keep the solvent is the amount of data, the increase in the size that you need. So, right. So do you have an estimate of how, I mean, then it's a question of even a supercomputing center could not offer you enough space to store those.
Yeah, it's not just the supercomputing center, it's also the efficiency in the way that we are retrieving data from these databases. So adding this large amount of solvent, such as the number of water molecules that we are now using in our boxes, it's really, really tremendous difference between what we are now storing and what we should store with water molecules. So yeah, I don't have the numbers here, but I don't know. I don't want to give you a number now, but it's large, the difference.
Okay. So there is also another question by Christian Sommer Tigerson. So Christian, if you unmute yourself.
Yeah. Okay, can you hear me?
Yes.
Yes.
Okay, so thanks for a very nice presentation. I was wondering, because I'm not really from the field of molecular dynamic simulation, so I was wondering how unique is what you have there, what you've been presenting now. Is that quite unique, or is that something that exists several places in the world?
If you mean the repository of MD simulations, as I was saying, now there are different initiatives that are starting to come up about these kind of repositories, but it's unique in the sense that when 10 years ago, when we started developing this molecular dynamics extended library, I think that in the whole world there were just 3 initiatives, and they all didn't succeed. They all didn't succeed because of the amount of data and the infrastructures that we had at that moment. Now it's it's similar in my way of thinking to the machine learning or AI. Now that we have really big data, we can apply this in a great way, let's say the AI and machine learning. Now that we have this kind of infrastructures, we can also start thinking about this kind of MD repositories. So answering to your question, is not unique, but we don't have yet a standard MD repository such as the PDBs for the static pictures of the macromolecular structures. And I think that the way that we should go is to have this standard repository for all the scientific community. And we are working on that.
Okay, so it sounds like the status on the molecular MD simulations and databases and infrastructure is similar to what we have for solid state materials, more or less.
Mhm.
Yes. Okay, thank you very much.
Okay. Yeah. Thank you very much, Christian. So we have another question by Salahuddin Sheikh. You unmute yourself, Salahuddin.
Hello, can you hear me?
Yes.
Yeah, so I am a first year PhD student. So my question is not about like something more deep into the molecular dynamics. So I have a question that is there a way we can like, do you have programs where the new PhD students, they can learn these techniques? So I have been working on molecular dynamics, and I am in my PhD, it's also about molecular dynamics, but it's coarse-grained. So I was very interested if I can learn all atom as well.
Are you in the biomolecular field or the materials field?
I'm doing kind of DPD simulation with fluid dynamics.
Okay,
So it's
I would recommend you to take a look.
I have applied also for your program in June. You have a workshop, but I'm not sure if I will. You have only like few, I don't know, 30 seats. So I was worried if I will not make it into the list, then yeah, that's a kind of issue.
Okay, I would recommend you to take a look at the different projects that you've seen in these two presentations, for example, in the NOMAD Center of Excellence and also in the BioExcel Center of Excellence. We all have a long list of training events. Of course, in SICAM, you can also find this kind of training events. So take a look at that and try to choose the one that fits your field, what you want to learn. But there's plenty of training events on this.
So the one you are doing it in June. So
the one that we are doing
also
in SICAM, in BioExcel, in where?
In BioExcel.
Okay, yes, that's fantastic. I have to say that's an amazing training. It's a whole week of training, not just molecular dynamics, also coarse grain, also docking, also free energy. So yes, I will go for this one.
Yeah, I have applied for that, and I hope for the best. Thank you very much.
Okay, thank you very much. I don't see any additional questions, so I think we can stop here. So thank you very much, Adam, for this very engaging presentation. And then we move to the third and last speaker of this first part of the event, that's Pierre-Paul de Broek from Louvain. So now the floor is yours, Pierre-Paul.
Thank you very much. So let's start sharing my screen. Okay, can you see my screen?
Yes, it's okay. Perfect.
So thank you very much for inviting me and giving me the opportunity to present here a talk instead of a poster. So I am Pierre-Paul de Broek. I'm a second year PhD student at Université Catholique de Louvain in the group of Gianmarco Rianese. And so I'm basically working on how to combine machine learning on material science. And I'm very excited to present you today ModNet. I will try to break down this title in the different parts that is made up of. So basically how we make accurate and interpretable property predictions by feature selection and joint learning. So my talk is ordered as follows. So I'll start with a brief motivation, and then I will present the ModNet itself, a bit of technical methodology behind this, and the results we get out of this. And then finally, as pointed out earlier in Claudia's talk, it's also important to really assess how qualitative these predictions are, and we'll talk a bit about how to assess uncertainty. So the starting point is a bit the last cloud we have seen about artificial intelligence. And once we have quality and fair data, we can train a model that based on either a composition or a structure, we predict, for instance, the refractive index or the band gap or any other property. So learning here means that given data, we get some accuracy. And if you provide more data, you would improve the accuracy of your model. So this workflows enables then to make thousands of predictions in a fraction of time. And so you can screen potential candidates. Of course, it's an approximation in your model. And then at the further step, you could perform DFT calculations, even experimental calculations to validate potential candidates. So, of course, there are also a lot of models that perform this kind of workflow in the literature, and I like to organize them in two different categories, where you have either ad hoc models where you have a very specific task in mind. For instance, you want to predict the band gap of binary oxides, and you would, by domain knowledge, engineer features and a model that is known to be performing well on this type of problem. And then even with some limited amount of data, you get good accuracy, but it lacks generality. So therefore we have the second group, which are basically deep graph networks, where you have a crystal that is then transformed into a graph. You perform a series of convolutions and you predict a final property. It's a very powerful technique because you have basically only the structure, the atomic numbers and the positions as an input. But in order to really learn this complex mapping, you typically need 10,000s of data points. And in reality, what you see is that most data sets we have are quite limited and below this threshold. So for instance, on the vibrational thermodynamics, on which I will come back later on, we have between 1,000 and 2,000 samples, which is really a limiting factor if you want to apply these deep graph convolutional neural networks. So this motivates a bit the need of having something that is working well on limited data sets. And this is how ModNet was a bit born. And there are also three other models I want to cite here is Automat Miner, CrabNet, and AtomSet, which are also recently developed and are performing well on smaller data sets. So let's start with ModNet. So ModNet stands for Material Optimal Descriptor Network. It's an optimal descriptor in the sense that we will select a subset, as you will see in the next slide. It's a supervised machine learning framework. So the idea is that you give a data set that is labeled, you have either composition or structure and accompanying properties. And everything is available on GitHub. So it's meant to be reused on your problem. So I will put a link at the end of this talk to the repo. Okay, so let's start by the workflow of this model. So we first start off by computing a huge amount of features from composition or structure. So for that, we use MatMiner. So it will generate composition, structure, and site-based features. And the idea is that compared to deep graph models, where you only provide an atomic number or a bond length, here you have something that is already chemical or geometrically meaningful. And so when you have limited data, it's much easier to map something meaningful to a final property than start from only atomic numbers. So in a sense, compared to deep graph models, we have already pre-learned features, which is an important fact when you're making models on limited data sets. So like I said, typically the amount of features we have here is too large. So it can range to easily 5,000 features. And so if you don't want to basically suffer from the curse of dimensionality, you need to be at around 300 features as an input space. And so we will perform feature selection. So how does feature selection works in ModNet? We start from all the features at our disposal, current feature set, and then for each feature in the feature set, we will compute a score, the RR score, so it stands for relevancy and redundancy. So the idea is that given a new feature f of x, you will compute the normalized mutual information. And so this measure is described here. It's based on the mutual information. So this is a normalization, and then the mutual information computes the difference in information entropy of your random variable x and the conditional probability of x given y. And the idea is that this will measure the relation between two random variables. It's similar in interpretation to correlation, but goes beyond by taking any nonlinear relation into account. And so when you have a good relation between a candidate f of x and target y, you will have a high relevancy. And so the upper part here will be high. But if you would see that some existing features f of I in my set would be also related to this new potential candidate, well, this would penalize this whole thing here, and you would have a lower score. So the idea is to really balance relevancy of the feature and redundancy, to have really a set that is not only relevant, but also redundant, to have a complete description to make your fitting. And so you end up with a list of features. So I want to briefly explain the advantage of doing a selection instead of an extraction. The main advantage is that you, of course, get interpretation from the features. So for a reminder, extraction is the idea that you would have a set of features and you would combine them potentially in a non-linear fashion to make new features that have lost interpretation. And so here you have 4 subplots that present 4 different properties: vibrational entropy, refractive index, formation energy, and band gap. And you see them here in function of the first selected feature. And then you have the second selected feature, which is not the most important one, but the most relevant and not redundant, as a color on these subplots. So you can find trends that are especially visible for the vibrational entropy and the formation energy that follow common intuition. So you retrieve the fact that vibrational entropy is dependent on here a feature that is in fact the inverse bond length. You have here the p-valence fraction, which is related to the bonding type, electronegativity for the formation energy. And so this confirms that your machine is making choices that are intuitive. And then secondly, given important features, you could actively create new features that would make more sense. So if we know, for instance, on the refractive index that this feature, which is in fact a weighted mean of the composition inside your structural composition of the band gap, so it's not the real band gap, you could say, I want to add the real band gap of my compound to make my model better. So that's an idea to improve your model thanks to the knowledge you have from the existing features. Thirdly, you can also see that it can happen that you have some gaps inside the range of important features. And so potentially it could be a good idea to add samples here actively to improve your model performance. And you know that you can retrieve samples by knowing the features you have to add. And then finally, when you would do any kind of post-analysis on the input state. So for instance, when you do a PCA on the input space, you can, or you keep understandability because your input space was already understandable. So I will show at the end of this presentation a little PCA example where you can see how we keep interpretability. And so finally, a last key ingredient of ModNet is the fact that we use a neural network that has a joint learning architecture. So the idea is that you don't learn only on one property, but on a set of properties. And this has 2 advantages. So of course, you gain time on the fact that you don't have a single model for each property. And then secondly, it acts as a regularization because these layers are shared among different properties. It's a bit like you would do transferring and reuse the same layers. They have to be general, and this will lower your test error. So let's now see a bit how this works in practice on results. So I've applied ModNet on a data set containing vibrational thermodynamics which contain not only one property, but you have a range of properties at different temperatures. And so it's a good example to train ModNet, because you can either train it on the vibrational entropy at 305 K only, or we could also include all the other properties at all the different temperatures, and this would then make up the multi-target ModNet. So the ModNet is only, like I said, one property. Then I have other algorithms you may know from the literature. So I want to briefly show the main results. And so the idea would be to compare ModNet against the multiple ModNet and the AllNet, which is ModNet without feature selection. And so here you have, for this property, the distribution of errors. And you can see that basically when you compare these three, you would have a 12% gain on feature selection, 8% gain on joint learning. And so this is really an advantage giving on this learning. And to give you a concrete example, we observe a 9 micro EV per Kelvin per atom error on this property. And you can see here typically what it gives. So it's on lithium oxide, which is a good example because you have the average error on this plot is about this MIE. And so you can really see how good this prediction can be. Then an important point I want to mention is that, of course, when you have models and you just give scores about how good or how bad they are, it's important that you do things in a systematic and concise way, in the sense that when we benchmark a model, it's good to do it on a series of tasks, so on different data sets, but also always use the same training and testing samples. So that's why now there has been MatBench, which is a standardized suite of 13 material science specific prediction tasks that cover different amounts of data, experimental or simulated, different kind of properties, and also cover classification tasks. And so it's a general good idea if you have a model to run it on this benchmark to compare it with existing models. And so here I show you some scores. So it's always the mean absolute error of ModNet on classification tasks. So on the experimental metallicity and the glass forming ability, it's an area under the ROC curve. So it's a higher score is a better score here. And what you can see is that we are getting good performance, for instance, on the experimental band gap with an error of about 0.35 EV. And in parentheses, you have the error you get if you even further tune the hyperparameters, being the learning rate, the activations inside the neural network. So also interesting is to see on the experimental metallicity, we are also getting good results. So really in the smaller regime, the results are rather good. So I want to now to briefly go to the next part, which is what about uncertainty? So up to now, everything was deterministic. So we have single predictions out of our neural network. But in practice, and as you can see from these graphs, we see that errors can vary quite significantly. So it's right tail distributions, which can go quite large. And so you can really have bad predictions. And so like we saw in Claudia's talk, it's not only, it's really about the quality and how we can assess them, especially if we are more in this extrapolation region and we don't really know how well the model will perform. It could be a good idea to have an idea about how good the model is performing. And so ModNet has been extended to 2 new frameworks. So the first one is a Bayesian neural network. So we replace the architecture you saw before by Bayesian architecture. So the idea is that weights are not deterministic, they are not single values, but are distributions from where we will sample the weights. And therefore, what you get up in the predictions is not only a single value, but a range of values. It's a distribution. And so the mean of this distribution would be the value you would use, and then the standard deviation would tell you how certain you are about that prediction. And so that's a bit the idea you see here. So if you would have these black points as training data, you would have a red curve, which would be your model. And then you see that, of course, the uncertainty in purple here would increase around unknown or far away from your training set, with the extra thing that inside Bayesian models, you can divide uncertainty in aleatoric uncertainty, which is uncertainty due to the fact that your data is noisy. So you can see that for one given value here on the x-axis, you have different observables. And so there is intrinsic noise, which is aleatoric data. And when the model is far from a region it is fitted on, it's of course in an unknown region, and your model cannot be trusted, and you have epistemic uncertainty. Okay, so another model extension of the original ModNet model is the bootstrap ModNet model, where you would bootstrap data in order to have an ensemble of ModNet models. So the idea is depicted here in this picture. You have your original data set, and then you will each time remake a new data set, which is sampled from the original one with replacement. So you can end up with multiple times the same compound. And then on each of these individual data sets, so I have depicted here 3 bootstraps, but in practice, it's much higher and can easily go to 100 models. And then you fit a ModNet on each of them. The models are also retrained, so you can potentially have different initial weights. And the thing is that each prediction at the end will be different. And so when you do that, you have statistics about all these models. You can compute the average, the standard deviation, the confidence, 90% confidence intervals. For instance, if you have 100 models, the 5 worst and the 5 best predictions you remove, and you end up with the 90 predictions, which would give you like an confidence interval for that particular prediction. And so with this method, you would have the idea that if all models have the same prediction, you're quite sure that this value is trustable because they have all predicted and converged to a single value. But if you have a prediction that goes to any direction on all the different submodels, you're basically unsure about that prediction. Okay, so here is an example in practice. So this is the refractive index data set, where you have here the true values and then here the predicted values by ModNet. And you can see that this bar is in fact something that is predicted by the model itself and knows that basically when you are far from the reality, you can see that it most of the time also knows it and predicts it. And so this can, in more technical terms, be assessed in a calibration curves where you compare the predicted proportion on the real observed proportion. And if you're close, you know that the uncertainty is an honest prediction from the model. And so probabilistic models are, I think, really important when you do machine learning, because it's also the basis of autonomous systems. When you have models that know when they are not good in their predictions, you can typically then maybe go back to a classical DFT calculation and then actively improve your data set and hope that this new sample can, of course, improve your model. And so I just want to end here on the idea on why would there be such differences in errors inside machine learning. Well, basically it's all about training and testing. So when you train on one space, and this would be then a two-dimensional visualization of your material space, when you are in one region and you want to predict another region, you would either have imbalance or bias of your data set. And of course, when you're far from the original space, you from the training space, you get bigger errors. And this is seen in practice. So I like this plot where you basically see the same refractive index data set. You have in blue the oxides, in red the non-oxides. So basically where you see the point is how it differs from other ones. And in dense regions, you get better errors than in more sparse regions, because there you have less training neighbors to get good predictions. And you can see that here every point is a two-dimensional object with a second component linked to the mean bond length and the third component linked to the electronegativity. So this ends my presentation. So I hope to have shown you that based on the amount of data, of course, you have to make a distinction between physical feature-based methods and graph-based methods. We get a good gain from feature selection and joint learning. We can assess uncertainty either qualitatively by this test training dissimilarity in a PCA decomposition, quantitative by using either bootstrapping or Bayesian models. And so this QR code is taking you to the GitHub page. You can always contact me on this email address. I want to thank, of course, all the people who have helped to make this model. So Gianmarco Rianese, Geoffroy Thier, and Matthew Evans, which will make a poster after this main event on Optimate. So I would check that poster out. And I thank my funding, the computational resources, and the university. Thank you.
Thank you. Thank you very much, Paul, for the presentation. So as we have done with the previous two ones, to talk, you can indicate if you want to ask a question simply by marking it through the Q&A channel, and then I will give you the word. While we wait for the next the question, in a way you have been. There is. I wanted to know how much feeling you get about the size. You have talked about the use of these tools to be able to operate with smaller data sizes and then be able to extract information. Do you have a feeling about, or I mean, for this type of situations you were analyzing, what would be a minimal set, or how much you can reduce by using one type, I mean, this deterministic or the probabilistic approach?
So really where we are targeting now is, like I said, is a bit about the limited space. And if I would put numbers on it, is around 1,000 and 5,000 to 6,000 data points. When it's too small, of course, it's too small. And the good thing about the probabilistic models is that, for instance, the bootstrap one, which is this one, it's just a very easy generalization of the modnet I've presented in the beginning of my talk, where you are not really limited on the data size, and so it's easily put in place with some confidence as extra output. The Bayesian modnet I found in practice to have a little bit more problems and really having the same accuracy I would have from a deterministic model. And so, yes, this is what I can say. Okay.
Thank you very much. So there is a question by Luca Gringelli.
Yeah. Hello, can you hear me?
Yeah.
Yes.
Okay. Hi. So thank you for the presentation. We had a contact a while ago about this project, so I start a little bit knowing what you would be talking about. So my point is on the interpretability of the network. So there is a kind of discussion in general field of artificial intelligence, but could be particularized to the scientific application. So there is a direction in artificial intelligence, of course, one I'm trying to pursue, where you have models that you can somewhat look into their face. You have equations, so besides the work we are doing in the Nomad laboratory. There is this Feynman, what is called Feynman AI. So they are trying to recover the famous equations in physics from the data with as little ansatz as possible. So with neural network, you always have this problem, or maybe it's not a problem, but you have a fact that it is very hard to know what it is actually doing. So I mean, you cannot follow the logic inside unless it is extremely simple. And I feel that there is the kind of perception that you will never know if it is reliable on an extensive scale. Like you can always plug in a data point and you get bogus result, and there is no way you can predict that. While if you have an equation or something that as a physicist you can kind of manipulate and touch in some sense, you have a feeling where you shouldn't go or like this. So I would like to have your comment about this.
Yeah, but I think your comment is really true, that beyond the fact that we can play a bit with the fact that we put features we know that should make sense on the fitting itself. Once you're in this neural network, everything is not interpretable. So you cannot look at the weights and say, okay, this weight makes sense. So this is, I completely agree that from the whole fitting part, it's a bit magical, but that's a bit, yeah. The thing about neural networks that they have good accuracy, even given the fact that they are quite complex with a lot of weights, and which is quite surprising. So I totally agree with that, and this is a limiting factor on the neural network. But I really like the last thing we did in our group on the bootstrapping method, where we have different models. And I think that if we have 100 models that are all giving the same value, we can normally be confident. And then if it's garbage, it's probably having very different results. But I totally agree that neural networks are really limited in terms of.
Yeah, I totally agree on the bootstrap thing. But I also see positively this thing that you reduce the number of features, right? So even if you do not know exactly the kind of functional relationship, you still say, okay, these features are important to give me my prediction. All these other features, probably not. So there is still some kind of safety, because imagine that you put noise or completely irrelevant features just to test your approach. If this irrelevant, or did you expect that they're totally irrelevant feature are selected, you will start saying maybe something is going wrong, maybe something in the data that is not. But if they make sense, at least you could be confident. Yeah.
The thing, it's a bit automatic, so we cannot systematically check they all make sense, but the idea is...
That of course, yes, but at least having few features probably is already something better than just plugging in everything and hoping that it works.
Yeah, and like you said, I think it's also a balance between often understandability and accuracy, because I think, of course, CISO, for instance, is of course more understandable than this approach, but then you have, of course, a trade-off between performance, so it's always a bit... probably a trade-off between all these things.
Yeah. Okay. Of course. I mean, the more things become complex, the more the accuracy is an issue. But it is also true that if I mean, imagine that you want to rediscover Coulomb law, and you plug in distances and charges, and then you have in your vocabulary in the inverse square distances and products and so on. And at some point, the Coulomb law is exact. Up to some, right? So it should fit exactly the data. So it's not a matter of simplicity or not. If you do the same with a neural network, you could probably still get the exact prediction, but you would still think, okay, but what exactly is going on in my network?
Okay.
Right. So
that's very true.
Yeah.
Totally agree.
Thank you very much. I do not see any additional question. Yeah, okay. Yes, there is one by Sandeep. So please, if you unmute yourself and ask your question.
Thank you very much. Actually, I have a question. Means, can we use this mode net? Let's say we have 5 target properties. Can we use this mode net? Let's say we have band gap, formation energy, and some other thermodynamic properties, and they are related to some structure parameters. So can we use at a time? Because it's easy to handle one target property, but if we have multiple target property, is it good idea to use Mornite or some other way? Can you explain something about it?
Yeah, so I'll go back to the joint learning part here. Yeah, so the idea is that, of course, you can put different properties and they can be quite distinct in terms of physical similarity. So two comments about that. So the first one is that we need, and this is a constraint, you need to have all these properties for one material. So it's basically an intersection between all these compounds. So if you have for one compound only the band gap and not the formation energy, and then the same for another one, you need to have all of them to make the fitting possible. And then the idea is that if you choose, and this is the hardest part, you have to optimize correctly the neural network to have this trade-off between sharing common information and not be too limited by this architecture. You can really observe an increase in performance you're getting out of the predictions.
Okay, and thank you. One more thing means, and how did you generate the data means so we can say that it's reliable means did you use what method you use to get the data means you have only the small database, but how can you say that it's reliable? Did you check means I just wondering about it.
So at this stage I'm using data that has been published and being on the materials project, and we have confidence on them. So I'm not directly assessing how reliable it is. Of course, it all depends on where it comes from. Is it experimental? Is it so here we put two experimental data sets and simulated ones. We also played with the multi-fidelity one of Shu-Ping-Ong, where you have band gaps and different functionals. So it is true that given the let's say the goodness of the data, it can be very different in terms of predictions. But I think you could probably also, an idea would be to put the multi-fidelities as different properties, or see with the uncertainty what you would have on for instance, different functionals. I don't know if this answers your question.
Okay, thank you very much. So,
okay, there is also another question by Christian Sommer. Please, Christian, can you mute yourself?
Okay. Hi, thanks a lot for a very nice and interesting presentation. So you have all these features that you start with, as far as I understand, and then you do feature selection. But I guess an important part would be features related to the structure of your material. Is that correct?
So that's a good comment. So I think it's a bit idea of how important the structure is compared to only the composition in the model.
Yeah, because my worry is that if you need the structure, then somehow you need to know what the structure is, and that typically if you want to use this to find new materials, which I guess is one of the big sort of goals in the field, that we want to be able to come up, suggest, as Claudia talked about, new materials for particular applications, then you typically don't really know the detailed bond lengths and the structure more precisely, and you would, for example, need to do a DFT calculation to get it, and somehow that's what you're trying to avoid here.
Yeah, and so it's a very good question, because we have tried to extend. So first we did only work on the structure, and then we extended on composition. And so we can learn, of course, and we can restrict any problem to composition only if then later on the application would be composition only. And it's often quite surprising to see that, okay, so of course the accuracy is a bit worse, so we're getting a bigger error, but often it's not that huge compared to having the structure. So, for instance, I think one thing is maybe to make more benchmarks on really structure versus composition on the same data set, but here on the band gap where we only have the, so it's experimentals, we only have the composition. We have this this error, and we have another data set. So of course it's always dangerous to compare with also experimental band gaps with where we have the structure, and the differences are quite small. So of course, when you compare to the band gap with DFT, where we have much more, the error is of course much lower, but it can still be surprisingly good on composition only. And so it's possible to do it.
So that somehow relies on, if you go directly from the composition to something like a band gap, that there is a well-defined route, so to speak, that there is one structure that is really, I mean, that would be the most stable one, because typically you could have different isomers with the same composition, but different structures, and they could have very different properties, I guess. Yeah,
that's so. The question is, would the machine somehow intrinsically learn what is the structure behind the thing? We could play with polymorphs to see that.
Okay. Yeah.
Yeah.
All right. Thanks a lot.
Yeah.
Thank you.
Thank you very much. So I don't see any additional questions. I think we had nice discussions all along. So thank you very much.
Thank you,
Paul. So with this, we come to the end of this first part. I wanted to finish by thanking you for attending, staying here this session, and I wanted to take the opportunity to mention that we have a next session in the month, the 6th of May. This will be on machine learning, and the expert speaker will be Michele Ceriotti from here from the EPFL, the thin line between physics and data. As I mentioned, the old information for the whole series is on the second webpage, and the past lectures and different presentations are made available, so you can go and watch also past events. And also, if you go to this webpage, you can register to the webinar mailing list if you want to keep or get information about this type of events. And I also take the opportunity to tell you that at Twitter, you can follow us at CCAM events in order to get updated with latest news on different activities that we organize. So with this, I thank you for joining us for this fourth installment. And remember that if you are registered, you can join us on gather.town now for the digital poster session. You have received by email the link, and then it's just by clicking or by copying and pasting that in your browser that you can access the Gather session. See you there.